Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Axiomise with Ashish Darbari. We're going to talk today about why proof conversion matters. Ashish, what's changed in proof conversion? Why does it suddenly matter?
Yeah, good question, Ed. So actually, not much has changed in proof convergence over the years. We told the world in that formal verification would get you proofs of bug absence. Tools have become a lot better, and a lot of technology happened in the tool stack. But a lot of the properties that formal guys write do not get a deterministic answer, which means that there could be bugs in inconclusive proofs. They're actually also known as bounded proofs. And we've seen that these things actually can cause a lot of pain to the end customer who has actually come to formal to get that extra mile on exhaustive checking. And I think every proof matters. The first bug matters and the last bug matters.
Where do you see AI fitting into all this?
And what we're seeing is, on the one hand, AI is being used to build better tools, better design. At the same time, the hyperscaler design companies are building AI accelerator chips. So it's a like complete reflexive, however you want to say, a closed loop system where we are using tools with some AI penetration to build better designs, do better verification, and to build what kind of designs? The ones that are actually going to be driving the tools themselves. So with AI, what is really nice is that you've got performance back, energy, power back, area back. So the three things that are important in PPA, besides the usual challenges of functional verification, which have actually been compounded. So there is a super exponential increase in complexity in AI chip verification. And the reason is, previously you had one core, then we became 4 cores or 8 cores. Now you're putting like 300,000 cores on a single die, let's say, or multiple dies on a 2D, 3D IC. A lot of the scenarios are now possible to see, which were previously not possible with just 1 or 2 or 8 cores. So now you're looking at AI chips burning away a lot of energy, causing PPA challenges. We've got chiplets in action, so you want to slice them off and fit them nicely so you can stack them on your 2 or 3D IC stacks. But at the same time, now you're seeing a lot more functional interactions. And bear in mind, functional safety has not gone away, security hasn't gone away. So everything is now amplified, and with a lot more money available for AI chip design, a lot more players are there. I should also point out that RISC-V is playing a very important role in this ecosystem, although most of the AI hardware seems to be on GPU side. But with all of this open source artifacts coming in, new developers are coming in, which may not have the verification expertise.
Well, let's take a closer look.
Sure.
Ashish, what are we looking at?
Right. So, Ed, this is the problem we are looking to solve. So, formal verification test benches are written using what is called assertions. We call them covers or assertions. I would refer to them as properties in general. Now, a lot of properties are written. They could be written by AI these days. They could be written by human experts through apps, for example, CDC, X-propagation apps, lots of apps. So this is the property generation area. Anybody could do this. But at the end of the day, we have to make sure that the chip can be signed off properly without bugs. So zero bug escapes is where we are trying to get to. The million-dollar question is, can we get from properties to sign off readiness with formal with a deterministic answer, which is a yes or a no? What I mean is that every property needs to either have a proof or a failure. We are not allowed to deal with question marks for sign off.
So how does this actually work? What are you really trying to solve?
Different designs have patterns. So you could have a GPU, you could have a NOC, you could have a RISC-V processor or an ARM or an x86. These designs serve different purpose in terms of functionality, but they all have a common pattern to them. We believe we have mastered the ability to analyze these common patterns between designs, so we could actually now ask the right questions through this framework, meaning we write good properties and build good models in formal verification. So we can actually get to the sign-off quality A faster, and B, get a yes or a no answer. So this technology that I'm talking about, which actually solves this gap in the middle, is called core proof. And what we do, Ed, in this technology is we are looking across the board, not just at functional verification targets, but also apps in general. So you have X propagation app that generates a lot of properties all the vendors supply you. These properties actually do not prove in practice. Can we impact the proof convergence? We built Footprint to actually do redundancy analysis on top of reachability analysis. Behind the scenes, of course, there is some property verification infrastructure that we built gets created. But there we are talking about a scale of 500,000, a million, 2 million checks. How do we cope with proof convergence there? So lots of different problems, but all have a common theme, which is get a yes or a no answer.
How far can you shift this left? Because further down in the flow, this doesn't really matter, right?
Right. That's a great question. So this is exactly where everything now comes together. So if you can actually check out an app as a designer to do your lint and a CDC and a reachability analysis and now the redundancy analysis with Footprint, you can find all of these issues much more quickly. And if you can fix these, then you actually know that the fix is the correct one. The problem you're going to have is, A, can you find all of these issues with a yes-no outcome? Secondly, if you fix them, can you prove the fix works correctly? So everything we are doing here is taking the verification to the not just the shift left. I would say it's taking them to the first week of design bring up. I understand, our friends in the customers would say, look, design changes. We don't know everything on the first day. I understand. However, whatever you know, if I give you the technology that gets you a yes/no answer, you can get much faster with knowing what to do to go to the next step.
A lot of these proofs have been sidelined for a while, right? What's driving that and what's changing?
So what's been happening is that formal verification in the hardware side picked up speed in late 90s, and then in the last 2.5 decades, a lot of very smart people who were doing formal have been trying different techniques on different designs manually. EDA has the ability to make more tools which can solve this problem, but we weren't really getting this convergence of ideas and technology. So most people have kind of resigned, in my view, on the promise of full proofs. And so you would see this term being talked about a lot, bug hunting, and saying it's okay to sign off with inconclusive proofs. We do end up signing off as well in some cases with inconclusive proofs, but we are very much driven to solve this problem. And why we are uniquely placed at is because our experience is hands-on verification on large designs with formal, but in the last 3 years, we've picked up speed building these tools and automating these technologies through this pattern recognition. So where we are is this human expertise in detecting patterns now being coded in the tool to give the acceleration that is needed. So we're still very much a human-driven effort right now.
So how does AI fit into this picture? In the past, formal and AI have been very separate worlds.
Actually, this is not entirely true, Ed. So, the seeds of artificial intelligence were sown in Turing's time, and in 1956, the Dartmouth Conference talked about reasoning and logic reasoning as a way of building ELISA, a tool that can talk to human beings. But machine learning in particular and the neural network side of AI was kind of seen separate to the logic reasoning. Actually, a lot of the people don't often know, but the formal tools we use actually have a lot of AI embedded in them, in the search techniques. But the generative AI, which is the new thing that's taking over the world, is a very fascinating thing with transformers and the like. And what we are seeing is that these things are in the early stages. They're shown to have some value in design and verification. But you have to seed these models properly. You have to train them on good data, because garbage in is garbage out. This is where our technology is becoming really handy, because we are distilling our human expertise into AI models, which can then train these models to actually start off on a higher note. We are guaranteeing that actually, if this is the design you bring in, if this is the test bench we write, you're guaranteed to get the sign off. If we put this in an AI model now, game on. So I'm very, very optimistic about where the two technologies are converging. It's going to be a game changer, because what we could do with human knowledge can now be accelerated with AI.
And this also speeds up formal too, right? I mean, one of the problems with formal has always been it's incredibly exhaustive, but at the same time, it's slow. As you put AI models in here, it changes everything.
Correct, correct. So agentic AI is showing a great promise in actually guiding interactively the end user to go in a certain direction. So everything fits quite nicely. So what we are doing is actually complementary. So we could seed the models, we could get you a great start. If the design is changing every day, the agents wake up and actually guide the designer. So everything is going to be several orders of magnitude accelerated. But the most important thing that we need to look on is we don't compromise on quality. So this is where formal becomes really handy. Hardest part about adopting generative AI is how do we know the models are not hallucinating? And this is where formal should be used. So if you're writing the properties to achieve sign-off and the LLM gets you an outcome, we can very quickly go back and prove them. Formal is the only technology, as you know, that can get you a yes or a no answer, provided we solve this problem, coming back to the original point. We could then also do what is called explainable AI and make sure the models are giving the right outcome. So I think you would see, I believe in the next 5 years, the convergence of formal and AI to be the most important development in our industry in a long time. Because although simulation models can also be accelerated, coverage can be accelerated with AI, but you then have the problem of how do you know the models are not hallucinating. Whereas in a formal framework, you get guaranteed outcomes, provided you know how to get guarantees. So it's all quite exciting and interlinked into each other.
And one of the causes of hallucinations is that there's not enough data, right? You really don't understand what's going on, and AI will make it up as it goes along. This sort of gets around that by saying, this is exactly what's here. We know it. We know exactly where the data is going. We know how it's moving. We know what's going on inside the chip.
Yeah, great question. So again, going back to DBCon, a lot of the AI companies who've got AI on the tin, they all know that actually the data that comes out is not always correct and there are hallucination problems. One conversation in particular was delightful. One of my contacts was using AI in formal, and somewhere along the line during the debug process, the agent said to this guy, you know what, I've actually found a solution to your problem. I know exactly where you're getting this failure, and here is the magic sauce for fixing it. And the agent said to this person, just disable this assertion and your problem is gone. This is like the classic hallucination problem you could think of. The model thinks that actually the problem is the question itself. So get rid of the problem, and now there are those solutions required. I think as we mature the underlying technology and the models have the way to say, I don't know anymore, please try it, or actually better yet, if they actually can feed formal back in the loop in the background, then I think you have a very solid combination. But the challenges I see is that the companies who are building very good agentic models are not the formal verification companies. Formal verification companies don't necessarily have the same know-how as the AI companies. I think it's converging, it's going the right direction, and I think that would be a good place. And then who owns the model, right? So neither the AI company nor the EDA company has the ownership of the design models. And as we all know, the more you can train, the more you can make the models better. But can an AI or an EDA company take one sort of designs from one customer and mingle them with another design from another customer? That is going to get lawsuits going, right? So it's going to get a little bit tricky to do all these compartmentalizations of different models. And this is where I believe doing some fundamental research almost on a whiteboard to understand how proof convergence can be impacted independent of AI in the first place is how we wanted to solve this, because we can then see we don't necessarily need to train the models in every design because we kind of know that the fundamentals would work across the board. It's a bit like synthesis. If you think of the synthesis algorithms back, you don't need different synthesis algorithms for different designs. You have a single compiler that can synthesize all kinds of designs. I believe the proof convergence technology we're building is going in that direction.
One of the challenges with formal is that there's really no benchmarks here, right?
You're absolutely right, Ed. So, you have it in the model checking competitions where they benchmark the SAT solvers. But actually, we were thinking about it, just like you have performance benchmarks for a lot of chip designs, we currently have no such a standard. Ideally, what would be nice is to say, if we have a solution to verify a knock and someone else has a solution to verify a knock, what aspects of knock were verified by which solution under what configurations, similarly for GPUs, for CPUs, and that would give everybody a clarity on this solution is best fit to solve this problem. Actually, this might be an area where I believe the industry could collaborate more, and we can put together a set of benchmarks to calibrate the solutions. Because one of the problems you see with formal is people say, we've proven it. What have you proven? Who has actually done the review? Even if a human in the loop was involved, did the human being reviewing it had the complete context? Context is becoming more significant in the AI domain these days, but if you look back, even in our human world where there was no AI, context was everything, right? And having that person with the deep context knowledge is the most important thing. So benchmarking would allow us to calibrate different tools, different apps, different methodologies in a more uniform way. How exactly would that happen? I don't really know right now, but it would be good to drive the industry towards that. That's a great question, Ed.
And that context can be, it could be a domain, it could be a workload, it could be all
Absolutely.
interactions with different devices too, right?
So many different things, isn't it? It's the domain itself, time to market, how quickly you can get the results, the quality of results, whether you're getting the right results. Proof is the proof for the right reason. Are you getting the coverage? If you inject the bugs in the design, do your properties fail? There are about less than 10 different factors that can actually be used to measure the quality of overall work. But the best one would be to see whether you can even crack the problem in the first place and you ask the right question, right? Writing very simple, naughty properties isn't going to actually be the breakthrough that the industry needs. AI agents currently are writing very simple properties, is what my sense is.
So tying this all back together, really what you're saying is that the benchmark can be used to tie all this data together, right?
Yeah, absolutely. So exactly. So if we have that kind of a uniform data, which we can label it properly, can make it more structured, we can bring it back to the AI models, and that way the models could be trained more effectively, and I suppose they would work more effectively. I think that would be quite a nice union of these things. Yeah, you're right.
Ashish Darbari, as always, thanks for a great explanation.
Thank you, Ed. Thank you very much.